Section 6.3, part 2. At this point, we just need more examples of using the multiplication principle, so let's do some more. Example 3. Diners at Angelo's Spaghetti Bar can select their entree from 6 varieties of pasta and 15 choices of sauce. How many such combinations are there that consist of 1 variety of pasta and 1 kind of sauce? So in this case, we need 2 choice blanks. So this one represents the pasta, first one, and the second one represents the sauce. So we know that there are 6 choices for pasta, followed by 15 choices for the sauce. So our first task and our second task. So altogether, 6 times 15, which comes out to be 90. So there are 90 different ways you can have 1 pasta and 1 sauce at this site, at the spaghetti bar. Example 4. 3 dice are thrown. How many different outcomes are possible? So here's my first dice. Here's my second dice, and here's my third dice. And again, they're just choice blanks. They're just ways to bookkeep things. So when I toss a single dice, well, a die has 6 sides on it. So tossing 1 die has 6 possible outcomes. But tossing the second die has the same 6 possible outcomes. And tossing the third die has the same possible outcomes. So the number of ways to toss 3 dice comes out to be 6 times 6 times 6, which is 216 possible outcomes for tossing the 3 dice. Number 5 goes to talk about area codes or zip codes. So zip codes start with a 5-digit number. So for part A, they want to know how many different 5-digit zip codes are possible. So 1, 2, 3, 4, 5. Now when they talk about a digit, right? A digit means a single number. And when you look at your calculator or your cell phone, the possible digits are 0, 1, 2, 3, all the way up to 9. So there are 9 of them plus the 0 gives 10 possible digits. So we talk about the number of digits. There are 10 digits that are possible. So there are 10 digits for the first on your zip code, 10 for the second, the third, the fourth, and the fifth. So altogether, there are 10,000. No, sorry. 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5. 100,000 zip codes are possible using a 5-digit number. Part B says, okay, well, how many are possible if we can't use 0? So how many are possible if 0 is not used as the first digit? So I'm going to do those choice blanks again. And I'm going to make a note to myself that this can't be 0. The rest of them can be any number we want. So if I take 0 out of the list, there are only 9 digits. Times the 10, times 10, times 10, times 10. So we again assume repeats unless it says we can't repeat, and there's nothing in the problem that says we can't repeat our digits. So we have 9 times 10, times 10, times 10, times 10, which comes out to be 90,000. So if you can't use 0 as the first one, then there are 90,000 zip codes possible. Okay, our next example says, 2 cards are drawn in succession from a regular deck of 52 cards. We are to find the number of ways in which we can obtain an ace and a king in that order. Before we go do that, let's just get a little bit of background and make sure everybody remembers their decks of cards. So there are 52 cards in a standard deck, card deck. There are 4 suits in our deck of cards, and those suits are a heart, a spade, a diamond, or a club. So there are 4 suits. And in each suit, there are 13 cards. So 13 cards per suit. And those cards are an ace, which can count as a 1 on the low end or the high end. And then you have 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The ones that are considered to be face cards are literally the cards that have a picture with a face on them, and that would be the jack, the queen, and the king. Now, we don't need all that for this problem, but just because we will need it in our probability section, there's a basic rundown of a deck of cards. That 4 suits times 13 cards per suit is how the 52 comes about. This particular problem is asking us, if we draw 2 cards, find the number of ways in which we can obtain an ace and a king. So the first card has to be an ace. The second card has to be a king in that order. Well, we have 4 aces in the deck, 1 in each suit, and we have 4 kings in the deck, 1 in each suit. So the number of ways we can get an ace followed by a king is 4 times 4, which is 16. So you can get ace of hearts with a king of hearts, and ace of hearts with a king of spades, and so forth. And that's what that is saying. Okay, example 7. Again, a very different problem. It says a row of 6 seats in a classroom is to be filled by selecting individuals from a group of 10 students. So I've got 10 students, but only 6 seats. So 1, 2, 3, 4, 5, 6 seats. Part 8 says, how many different ways can the seats be occupied? So I'm going to put these 10, well, I'm going to put some of these kids into those seats. How many ways can we do it? Well, when I go to put the first person in a chair, there are 10 to choose from. So I've taken one of them, I put him in the chair, but now I'm going to go back and pick another person. Well, now there are only 9 people left. So I've now put a second person in a chair. When I go back to pick another person, there are only 8 left, followed by 7, then 6, then 5. So notice it counts down because I've put a person in, I have less to choose from. And if you multiply all that out, it comes out to be 151,200 ways. So 151,200 ways to put to fill 6 seats from 10 people. Now part B adds on a twist. It says, if there are 6 boys and 4 girls, so 4 girls in the group, and if the boys and girls alternate, find the number of different seating arrangements. So I still have my 6 chairs, but now I'm going to have a boy followed by a girl, then back to a boy and then a girl, another boy and then a girl. So when I go to pick the boy first, I have 6 to choose from. But now I'm going to ignore the boys, go to the girls, and there are 4 to choose from. Okay, I've got 1 boy and 1 girl. Now I'm going to go back to the group of boys and pick, but there's only 5 of them left. Back to pick a girl, and there are only 3 girls left. Now I'm going to go pick a boy, of which there are 4 boys left. And then I'll pick a girl, of which there are only 2. So each time, you can see them counting down. So there's 6, the 5, and the 4. And then you can see the 4, the 3, and the 2. And if you multiply all that out, you're going to end up with 2,880 ways to put those 4 girls and 6 boys into the 6